Welcome back, everybody. We're going to continue with section 3.4. Zoom's being shitty right now. It'll unclear a little second. We've got some word problems in this section. So the first problem is we're gonna assume that a soap bubble retains its spherical shape. Did we do this one already? I must have not had the scan into the lecture notes. Let's try that. Like I remember talking about that. A boat's pulled into a dock by a rope. The rope is attached to the bow of the boat and passes through a pulley on the dock that is 1 meter higher than the bow of the boat. If the rope is pulled in at a rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? I'll give you guys some time to write that down. Then you're not doing this without a sketch. If you do this without a sketch, chances are you're going to have the wrong relationship and stuff. Something happened today? Where the fuck is everybody? Only half the people showed up today. A lot of people are online, but still. We're still at about half of the class. There's Matthew. Give you another 30 seconds to jot it down, and then we'll start with our sketch. All right. So it says there's a boat being pulled into a dock, and let's make it like a little pier. We got a little pier. There's some water going underneath it. There's a boat coming up to it. That's my water. My boat. This is a great boat. Look at this boat. Boom, boat. And it says there is a rope attached to the bow of the boat. So it must be a little like a ring there, and there's a rope coming off. And it's attached to a pulley on the dock that is 1 meter higher than the bow of the boat. So maybe there's a little pulley up like this. And cord's going over it, and it's going like that. And this is 1 meter high. It says that the rope is pulled in at 1 meter per second. So this is going at 1 meter per second, which kind of means that's going at 1 meter per second. Says the rope is being pulled in at 1 meter per second. How fast is the boat approaching the dock when it is 8 meters from the dock? Which means this is 8 meters. I think we need to assume that the pulley is at the end of the dock. Let's assume the pulley's at the end of the dock. Which makes sense. You wouldn't have it like inland more. You'd have it at the edge. So we want to know how, our question is, what is that speed? How fast is it going there? So those of you that just got in, I'm gonna put the question back up on the screen for a second. You wanna glance at it, read real quick? Or take a picture with your phone? This is what we just got done drawing. Okay. So what do we got here? We got a triangle. I got a triangle here. Let's enlarge that triangle and get it out of the picture. This is 1 meter high. This is 8 meters long. And so I think we can figure out this length right here, right? Let's figure out what we can, what we know. X squared plus y squared equals z squared, or a squared plus b squared equals c squared. Let's use the letters you guys know. So I'll call this A and we'll call this B. So 64, which is A squared, plus B squared is 1, is C squared. 65 equals C squared. So C equals plus or minus the square root of 65. Which one is it? Dalton. It's got to be the plus one. Yeah, it's a distance. It's a length. It's a measured thing. We'll put in square root of 65 there. All right, so the other things we know about this triangle are this is changing at 1 meter per second. And this is what we're looking for. Well, we could do these things are changing with time. So we could take the time derivative of this equation right here. But we gotta do it implicitly, the implicit differentiation. So when we take the derivative of a squared gives us 2a dA dt. And b squared gives us 2b dB dt. That sounds weird. And c squared gives us 2c dc dt. Maybe I need to label these right here. A was on the bottom, so this is dA dt. dB dt is right here, and c was the hypotenuse. Make sense so far? So we're looking for this. This is what we want. We got to try to fill in everything else that we have. We have A. A is 8, so I've got 2 times 8 times dA dt. And then I've got B. B is 1, so I've got 2 times 1. What's dB dt? Dumb. Exactly. The pulley's not moving. It's stuck on a pole, so like its height's not changing. This is 0. So that's 0. C we had was a fun square root of 65. And dC dt was 1 meter per second. We know this is all going to end up in meters per second. So what do we have when we clean this up? I've got 16 dA dt, which is what we're solving for, equals 2 root 65. Maybe I'll keep my units in there. I think it's kind of helpful. That was 8 meters, so this is 16 meters. That was square root of 65, so this is square root of 65 meters. And then we got the meters per second. So this is effectively meters squared per second. It helps to make sure you have your units in there when you can. That way you can make sure you got the right units at the end, make sure it makes sense. We'll divide by 16 meters. So dA dt equals 2 over 16 is the same thing as 1 over 8. This is square root of 65 over 8. And I've got meters squared on top, meters on bottom. That ends up getting us down to meters per second, which is what it should be, because the rope is moving in meters per second, so we should have the same units. And if you do square root of 65 divided by 8, because that's meaningless to me, it doesn't tell me how quickly it's moving. I don't know about you. This is approximately 1.00778 meters per second. Any questions? I need to get you a new beanie, Dalton. Fucking thing's creepy as fuck. It's like a eye magnet. I look up and a fucking Sauron's staring at me. All right, you guys ready for another one? All right. Wall of text attacks you. Television camera is positioned 4,000 feet from the base of a rocket launching pad. The angle of elevation of the camera had to change at the correct rate in order to keep the rocket in sight. Also, the mechanism for focusing the camera has to take into account the increasing distance from the camera to the rising rocket. This all makes sense. It's got to keep focusing. Let's assume the rocket rises vertically and its speed is 600 feet per second when it has risen 3,000 feet. How fast is the distance from the television camera to the rocket changing at that moment? And if the television camera is always kept aimed at the rocket like it should be if you're fucking filming a rocket launch, how fast is the camera's angle of elevation changing at the same moment? I feel like it should be going like 4,000 feet is like 80% of a mile. That camera's quite a ways away, which it should be. Like fire and shit shoots out of the bottom of the rocket. You can't have the camera next to it. Does anyone need that up longer? It's like Edgar's still writing. For those of you that did the makeup exam, I'll be going through it this weekend. So you'll see an updated grade. Correct. Let there be darkness. All right, everyone ready? All right. So we got a camera that is 4,000 feet from the base of a rocket. So let's say the rocket base was here. The rocket has launched up. It's going pew pew pew. It's got some fire shooting out of the bottom of it. And 4,000 feet away, we have Mr. Cameraman here. And he's filming that shit. And we'll make it go to the center of the rocket because that's where the camera would point. So it says this is 4,000 feet. That green pin's dead. Let me get a new one. And it says the angle of elevation of the camera had to change. So angle of elevation is this. I grabbed the wrong pen. That's my angle of elevation. It's changing, so it's going up as the rocket goes up. It says when the rocket is 3,000 feet in the air. So when this is 3,000 feet up, it's increasing at 600 feet per second. How fast is the distance from the television camera to the rocket changing at that moment? So we are looking for this distance right here. Let's call it X. So find the distance to the rocket. Which we've called X. And it says, if the television camera is always aimed at the rocket, how fast is the camera's angle of elevation changing at the same moment? So changing angle. So it's how much is the angle changing with time? So what is that asking us to find? Not just theta, but theta is changing. So d theta. All right, so we got a lot of shit going on here. Let's call the bottom one. We got a triangle, so we'll use A, B, and C again. We'll call that A. We'll call this B. Fuck it, we'll leave X. So I have A squared plus B squared equals X squared for my picture. I think we can answer the first question pretty quickly. This is the Pythagorean formula. We got everything but X. 4,000 squared plus 3,000 squared equals X squared. So 16 million plus 9 million equals X squared. That's 25 million. So X has got to equal the square root of that, which is 5,000. And that's in feet because the other two are in feet. You guys need more light, just wave your arms back there. Like, nope, fuck it, we're happy right in the dark. Cool. All right. That actually answered the first one. So we want d theta dt. Well, if I look at the triangle, let's see, what do we want here? Couple ways we can go about doing this. This is x. We have dB dt. We have that already. So it would be handy to have one of the other ones. We actually know dA dt as well. That's 0. And this is 600. Yeah. Find what?
The change.
Oh, yeah, it asks us to find the speed, it asks us to find dx dt. You're right, it did. How fast is this distance from the television camera to the rocket changing? That was not what it asked us. That was just something to go along the way. So changing distance. That seems like that'll be helpful. All right, well, we can do that. Let's hit this bad boy with just like we did last time. Hit that with some time derivative. dt. So I've got 2a dA dt plus 2b dB dt equals 2x dx dt. All right, A is 4,000, 4K. So 2 times 4K is 8K. dAdt though isn't changing. That's 0. B was 3,000 feet, so 2 times 3,000 is 6,000 feet. And dB dt is 600 feet per second. Looks like I'm going to do 2x dx dt over here. 2x is, x was 5,000, so this is 10,000 feet. dx dt. So I'm going to do 10, right as 10K, make it a little bit shorter. 10K dx dt. I've got 6K times 600 which would be 3,600 K. And this is feet squared per second. And this was in feet over here. So if I divide by 10K feet, uh, 360 feet per second. Okay. So now we need to find d theta dt. So we need a relationship between these. Which trig function do you guys want to use? Sine, cosine, or tangent? We have all the speeds. First person that says it picks it. No preference. No one gives a shit. All right.
Sorry.
Sine. Okay. So sine theta is opposite over hypotenuse. SOHCAHTOA. So opposite is b over x. I need a little more room, so I'm gonna do this. So we have sine theta equals b over x. And we're gonna hit this with the time derivative. Which means a fucking quotient rule on the right, doesn't it? The derivative of sine is cosine, so I have cosine theta and then d theta dt. And here we got high prime low minus high low prime over low squared. High prime is derivative of b, so I've got db dt times low, which is x, minus high, which is b, times low prime, which is dx dt, all over low squared, which is x squared. All right, let's fill in what we know. We know cosine theta. Do we? Can we get cosine theta? We can get cosine theta, right? Cosine theta is adjacent over hypotenuse, which would be 4,000 over 5,000, which equals 4/5. So we have 4/5 d theta dt. dB dt is the vertical change. The vertical change was 600 feet per second. We're multiplying that by x, which was 5,000 feet. I need a bigger fraction. And then I have b was 3,000 feet. And dx dt was 360 feet per second. And I have low squared is x squared, which is 5,000 feet times 5,000 feet. So I've got feet squared per second on top, feet squared on bottom. The units are going to end up being 1/s. All right, this is some messy shit. I'm going to go back to K. 5K times 600 is 3,000 K. Minus 360 times 3K is 360 times 3 is 1,080. 1,080 K over 5,000 K per second. I can do part of that in my head. 3,000 minus 1,080 is going to be 1,920 K divided by 5,000 K. The K's cancel. I have 9. If I multiply by the 5/4, I get d theta dt equals, the K's cancel here. This is like 5 times 1,000. The 5 will cancel. So I've got 1,920 over 4,000. .48. What are the units there? We just had 1/s. Dalton? It's gonna be related to angles, but whenever we use trig functions, we're using radians. You have the right idea, though. If you don't use radians when you're doing derivatives with trig functions, you have to put in a pi/180 fucking conversion rate. It's absolutely terrible. Because it's assumed the derivatives in the cosine and sine, or all the derivatives we calculated were in terms of radians. But right idea, right premise. It's kind of neat. So, like, if this wasn't a TV camera, if this was like an anti-aircraft missile or a surface-to-air missile trying to take out a rocket that's moving, if you know the speed of the rocket that's moving, it obviously wouldn't be coming up, it'd be on a different trajectory. But you can do some of this. This is how they calculate how to shoot down the rockets. The computer calculates the speed it's going, how quickly it'll take its own missile to get to the incoming rocket, and chooses the angle so that it'll intersect it using shit like this. It's all computer calculates it all out, but it's all done with these type of things. It's kind of neat. That's more war related than watching a rocket launch like at NASA. But is there any questions on that one? All right, let me give you guys one to struggle with. Write this down, then we'll draw a picture, and then we're gonna let you go. Or not go, like work on it for a bit on your own and see what you get. The satellite is in an elliptical orbit around Earth. Its distance r in miles from the center of the Earth is given by the equation r equals 4,995 divided by the quantity 1 plus 0.12 cosine theta, where theta is the angle measured from the point on the orbit nearest the Earth, which is called perigee. At the instant when theta equals 120 degrees, the angle theta is increasing at a rate of 2.7 degrees per minute. Find the altitude of the satellite and the rate at which the altitude is changing at this instant. All right, you guys ready for a picture? Nope, couple folks, all right. Okay, let's do a little sketch. It says the satellite is in an elliptical orbit around Earth. Let's just, I didn't change the camera over. So satellite problem. It's in an elliptical orbit around Earth. I first drew this, and then I realized this isn't right. Because, well, not the way I want it to be. It says theta is measured from the point on the orbit nearest the Earth, perigee. So if I want to treat theta the way I like theta, I gotta make it like a vertical thing. That way, that is the perigee. So this would be R. And it says at the instant when theta is 120 degrees, it's swept out to there. Degrees. And it gives you d theta dt is 2.7 degrees per second or per minute. They want you to find the altitude, which here is R, and the rate at which the altitude is changing, and dr dt. So with the right sketch, you've got what you need. Make sure you change to radians before you start using stuff. Alright, you guys ready? So 120 degrees is what in terms of radians? Two pi over three, since no one's answering me. This one doesn't get very friendly. 2.7 pi over 180. We'll need a decimal for it when we use it. So the first thing they wanted us to find was the altitude, which is R, and R was 4995 over 1 plus 0.12 cosine theta. When we do that at 2 pi over 3, let's see, this is, oh, I'm missing the 0.12 right there. Times that. So this is the reference angle is 60 degrees, cosine of 60 is 1/2. We're in the second quadrant, which would make it negative 1/2. So this is 1 minus 1/2 of 0.12, so 1 minus 0.06 on bottom. We've got 4995 over point, son of a bitch. Wait for it. It's all creepy dark in here now. It's fucking so goddamn loud. I don't know why it's so loud. 4.995 over 0.994. Not 0.94995 divided by 0.94. I'm getting R is 5,313 point, we'll just leave it at 8.8 feet. It's probably miles. I don't know why the hell it would be feet. That doesn't make any sense. It's gotta be miles. That's not even a mile up. Maybe I'll put all the decimals that I have here. We can decide on accuracy later. 829,787 miles. All right, then they want dr/dt. So I'm going to write R like this first. Because I hate doing quotient rule when there's just one thing on bottom. This is easier as a product, or not even a product, just a chain rule. You bring the negative down. The power goes down by 1. We take the derivative of the inside. The derivative of the inside is negative 0.12 sine theta. And then we take the derivative of the inside of cosine or sine theta, and we get d theta dt. So DRDT, looks like the two negatives cancel. I got 4995 times 0.12. Sine of theta is sine of 2 pi over 3. That's the numerator. The denominator is 1 plus 0.12 cosine of 2 pi over 3, that thing squared. And then I have d theta dt. And we already calculated this. This was 0.94, so we got 0.94 squared on bottom. Sine of 2 pi over 3 is the same thing as sine of 6 or pi over 3, which is root 3 over 2. So I've got on top, oh, and d theta dt is 2.7 pi over 180. I'll cross off d theta dt. We got a lot of shit going on here. Let's just clean this up so we can see what we're looking at. I've got 4995 times 0.12 times root 3 over 2 times 2.7 pi. On bottom, I have 0.94 squared times 180. Square root of 3 divided by 2 times 2.7 times pi. So on top, I'm getting 4403 some change. Four squared times 180. 159.048 on bottom. And so I'm getting 27.68 something. This is in miles per minute. Say 27.7 miles per minute. And we'll take this down to 1 decimal place too. All right, let's take a quick break, a 5-minute break, stretch your legs, go pee, get some water. We will start and hopefully finish 3.5 in a second or next. Okay, this is on 3.5. This is called local linear approximation. So what we did with the rates of change are called differentials. And one application of differentials is error propagation. The idea here is when we take measurements and stuff, The tools we measure with have only so much precision. Which leaves a small amount of error, hopefully small. In measurements. Anything we use those measurements in carries that error forward. It's called error propagation. It propagates forward. Now, usually our error in measurement is like going to be something like a delta X. If we're using X and Y, our measurements in X, but our calculations are in Y. The error propagates over here to something as delta Y. Or effectively dx and dy. So if we have y equals f of x, we take the derivative, but we're doing it as differentials. We get dy equals f prime of x times dx. So whatever our error is, our whatever our measurement error is, that's our formula error, as what I described up above. So it's modified or multiplied by this. It's called scaling. It's scaled by that. Wow, that was a nice one right there. You're smiling. It sounds like you look like you like it. Are you sicko like that? All right. Is anyone still writing this? Okay. Let's do an example. Let's say you've got a water balloon. And you like measure how much water goes into the balloon. Which we are going to pretend is spherical. And so to do that, you measure the radius of the balloon. You measure radius of the balloon. And your measurement says that the radius equals 3 inches with a possible error of plus or minus 0.1 inches. What is the corresponding error in volume? All right, so volume for a sphere is 4/3 pi r cubed. If we take the derivative or find the different, do this, take the derivative by using differentials. We have dv equals, we take the derivative of r cubed. This goes down to an r squared. The 3 comes down. 3 times 4/3 is 4. So we got 4 pi r squared dr. It looks like if we did the derivative with respect to r, oops, and then multiply by dr to do that. It looks like it, but it isn't. But discernibly, like being able to recognize the difference, there's no like realistic difference. So if you're comfortable doing dv/dr and then like multiplying, if you're not happy with doing this implicit differentiation, that works just the same when you're working with differentials. But you're better off getting practice doing implicit differentiation. So what we have here, we have dv is what we're looking for. 4 pi, the radius was at 3 inches. And dr was plus or minus 0.1 inches. So dv is 3 squared is 9. 9 times 4 is 36 times 0.1 plus or minus 3.6 pi inches cubed. And throw that in a calculator, dv is approximately 11 plus or minus 11.3 inches cubed. Now, we're gonna do it more on the next problem, but we can do it here. There's something called percentage error. Which is error over total. Which would be like dV over V for this problem. V, we don't know what V is, but we can calculate it. V equals 4/3 pi times 3 inches cubed. One of the threes cancels that. We've got 9 times 4 pi is 36 inches cubed. So the error here, oh, I'm missing a pi there. The total volume error would be, or percentage error would be 3.6 pi over 36 pi inches cubed. This looks like plus or minus 0.1, which is 10%. Plus or minus 10% error in volume. So like, this is the error. But that doesn't I don't really know how, like, what does that mean? If it's a big balloon, like how much water is actually in the balloon? Is it a lot of water? Is it like at a big error rate? Is it a small error rate? So when we do percentage error, this is the error relative to the actual amount. That way we can get an idea, like, is this a big error? Is it a small error? If this was 0.00001, where it was like, 0.01%, then this has got very, very low error. Having a 10% error in volume, though, seems like quite a bit. So this is more of a practical use. Percentage error tends to be more of a practical use. Or a more practical description than just the error by itself. Now, it is important to know here that the exact value of the volume wasn't known. I used 3 inches for R. But R could have been. R was within 0.1 inches. So R was between 2.9 and 3.1. But this percentage error is doing the percentage error is a good relative error approximation because we're pretty close. Since we didn't have the exact volume. If we had the exact volume, we wouldn't have this entire topic at all. All right, so next example. You are firing a cannon at a target. At an enemy castle. Fuck yeah. Let's destroy an enemy castle. The projectile speed or muzzle speed. It's got some boom. It's 450 feet per second. That cannonball's going fast. And we have the cannon sitting at, or you have the cannon at a 30-degree angle. With a possible error of 1 degree. What is the relative error in the cannon shot? And you'll need to know like the range. The range of the cannon is V naught squared sine 2 theta over G. Where V naught is the initial velocity. Theta is the angle of attack. And G is a gravitational constant. It has 2 different values for Earth. 1 in meters per second squared and 1 in feet per second squared. Since this is in feet, the gravitational constant is 32.17405 feet per second squared. So to do the relative error, we need both the range and then the possible error in the range. So we're looking for dr over r. That is our percentage error or relative error in cannon shot. and in shot range. So if we look at R is, let's list what we have here. B naught was listed above at 450 feet per second. And theta was listed as 30 degrees plus or minus 1 degree. Which is kind of like an x plus or minus a dx. Delta x. So our V naught squared is 450 feet per second squared. And then we're doing sine of 2 theta, which is sine of 60 degrees, which is pi over 3. And we're dividing by the gravitational constant. Write it down right, 405, yeah. When you calculate this out, the second square go away, one of the feet cancels, we're just left with feet. Do this again and make sure my initial calculation was correct. I'm getting 5,450.67. So that's the range I think my cannon's going. But if that cannon's a little bit down or up a little bit, we can figure out if we overshoot or under, like how much we could possibly undershoot or overshoot by. So we find dr with respect to theta. Going off of this equation up here. V naught squared is just a constant, so is G. We'll plug those back in a second. We're just taking the derivative of sine 2 theta. So I have the derivative is cosine 2 theta times 2 d theta. So we'll do this again. 450 feet per second squared. This is 32.17405 feet per second squared. Cosine of 2 theta is now cosine of 60 degrees, which is 1/2. And d theta, we want it in terms of radians because we don't want to have degrees in it. If we have degrees in it, it's degrees times feet. Radians are unitless though, so we're going to convert to radians. 1 degree is the same thing as pi over 180 radians. Looks like the 1/2 and the 2 cancel. Save yourself a little work there. So we got 450 squared divided by 32.17405. That's my coefficient. And then I multiply it by pi and divide by 180. (109.85 feet). And this was a plus or minus 1 degree, so plus or minus that kind of error. So if we want to find dr over r, our relative error, it's the plus or minus 109.85 over the whole range of 5,450.67. (0.0201 or 2 rounding). This is about 2%. 2% error in distance. Now, I don't know about you, for me, the cannon, I think I would rather care about the feet. If the castle's big enough, 109 feet, if I aim at the center keep, I'm still probably hitting the wall. You know, so I'm still hitting my target, maybe not like the central keep, but I can still take down the wall if I'm aiming right.
I have a question.
Yeah,
So how'd you get G? Why is it 3.32.17465?
that is an excellent question. Gravitational constant. Where is it? I want SI units, I want feet per second. Try this. Gravity. Measure. So in meters per second, it's that. In gravity, oh, they got a little slightly different value here. They have that. I saw the 0.17405 on another spot. But I just Googled it.
So let's say if we do another example where it's instead of 450, it's 500. Would we still use that number for G?
Yeah, the gravity of Earth doesn't change just because you change how fast you shot your cannon. Does that make sense?
Yes.
When if I say it like that, then you're like, yeah, that makes total sense. All right, we got one more problem in this section, but we don't have time to do it. So let's call it a wrap today. We will do it on Tuesday, along with, I think, one of my favorite topics in all of calculus, L'Hopital's rule. Now, GTFO. Yeah.